Welcome to yet another related rates example. So in this example, a movie is filming a plane taking off. The camera is on a track perpendicular to the runway and moving away at 400 feet per minute. The camera is also rotating to keep the plane in center view. And when the camera is 500 feet from the runway, the plane is 3/4 of a mile down the runway from the camera track and moving at 350 miles per hour. How fast is the camera rotating at that point in time in radians per second? So again, the first thing we want to do, if there's not already a diagram drawn for us, is just to kind of draw a diagram, figure out what's going on. So we have a runway. Here's her runway. And we have our plane going down the runway, heading in that direction. And then we have our camera track, which is perpendicular. Here's our camera. And our camera is going along the track away from the runway. And the camera is going at a steady 400 feet per minute. Okay, so this is kind of what's going on. And the camera is rotating so that it can keep the plane in its line of sight. So as the plane moves, as the camera is rotating. So I'm going to go ahead here and add in some variables. So we'll go ahead and label the runway distance, or from the distance from the track to the plane, as P for plane. I'm going to label the distance from the camera to the runway as C for camera. Then we have our angle for the camera, which is going to be the Greek letter theta. So this is sort of the information and the things that are changing for us. So if we just kind of jot down what we know and what we want to know. So we know that the camera moves back at 400 feet per minute. Right. Then what we also know is when the camera is 500 feet back, and the plane is 3/4 of a mile, then the plane is moving at 350 miles per hour. And then what we want to know is how fast is the camera rotating? In radians per second when the plane, well, when we have the camera 500 feet back and the plane 3/4 of a mile down runway. So just some things to watch out for in terms of units. For distance, we have feet, miles, and miles and feet, right? So just note that distance is in both miles and feet. So we need to convert to a common distance measurement or distance unit. So we'll go ahead and convert to miles. Then if we look at our time units, we have per minute and per hour and per second. So note that our time is in minutes, hours, and seconds. But the seconds is only our final target. It's only at the very end. And so what I would do is I would convert the first two into a common unit. So I would maybe convert into hours. And then at the very end of the problem, we will convert into seconds. So our little pieces of things to convert, we have 400 feet per minute. We need to convert that into miles per hour. So I'm first going to convert 400 feet per minute to miles per hour. So we have our initial units, and then we have our target units of miles per hour. So what we need to do is we need to have units cancel out using conversions of equal to 1 so that we wind up with miles per hour. So to get rid of feet, we're going to need to multiply by feet on the bottom to cancel out with the feet up top. And then we're trying to get to miles. We do know how to go from feet to miles. And so this will cancel our feet and feet. And then we'll do, to convert time, we will need to convert, we need to cancel out minutes. So we'll put minutes up top. And we do have an easy conversion, minutes to hours. So we can cancel our minutes that way. Let me do a different color. So this is what we're aiming for, just in terms of units. So if we put this back in just all together, we have 400 feet per minute times we have 1 mile per 5,280 feet. Then we have 60 minutes for 1 hour. And again, I have this set up. My feet cancel. The minutes cancel. And we are left indeed with miles per hour. And if we do that conversion, what we wind up with is 4.54, and actually the 54 is just repeating miles per hour. So that takes care of that first unit, right? That 400 feet per minute. Next, we need to convert the 500 feet. So we're going to convert 500 feet to miles. This one's much faster, right? We're just going 500 feet. Want to convert to miles. And we can do our miles over feet so that the feet cancel out. And that would indeed give us miles as our final answer. So we have 500 feet times, there is 1 mile per 5,280 feet. And if we do that math, 500 divided by 5,280 winds up being 0.9469, and the 69 is repeating. And then, so that takes care of our first 2 feet per minute, and then our 500 feet. 3/4 of a mile is in the correct units. 350 miles per hour is in the correct units. So we have everything that we're starting with is now in the appropriate units. So if we now rewrite what we know is now the camera is moving back at 4.54 repeating miles per hour. We also know, that when the camera is 0. Oh, sorry, I lost a 0. This should be 0.09469 repeating. 500 divided by 5,000 should be only a 10th, right? So again, when the camera is 0.094 and then 69 repeating miles back, the plane is 3/4 mile down the runway. And moving at 350 miles per hour. And then we want to know how fast this angle or the angle is changing. So the rotation, speed, camera in radians per second at that time. So this is a very important thing to watch out for. When we do these problems, our units need to agree. So it's very important that we look at sort of the units, get them all arranged before we jump into the rest of the problem. So again, our diagram we have our plane P, camera distance is C, the angle is theta, and our camera is moving this way at 0.09 miles, is moving at 4.54 miles per hour. The plane is moving, but it's not at a fixed speed necessarily. It's just at one point in time we know, and then our angle is increasing, presumably. So if we put all of this information in notation form or in symbols, the camera moving back at 4.54 miles per hour. The camera moving back, sorry, I also did my camera moving the wrong direction. The camera's going the other direction. Right? The camera moving back is going to be dc dt is equal to 4.54 repeating, and then that's in miles per hour. Okay, I was just checking that I drew my original diagram correctly. Sorry for this crazy scrolling. And then when the camera, so this will be in green, when the camera is 0.094 miles back, the plane is 3/4 miles away along the runway, and it's moving at 350 miles per hour. So now what's in green, we have the camera C is 0.09469 repeating miles. We have P is 3/4 of a mile, or 0.75 miles. And then we also have the plane is moving, dp dt is 350 miles per hour. That's positive because the plane is moving, the distance is increasing, the P is increasing, right? So all of this came from that green information. And then we want, so this is when this is true, right? And then we want the rotation speed of camera in radians per second at that time. So we want the rotation speed will be d theta dt. We'll start with that. That will be radians per minute, since t is in, this will be radians per hour, since t is in hours. And then we will convert to radians per second. And it's at the specified information, or at the specified time here, right? So this is everything we have in sort of formula. Again, notice that I'm specifying what units I'm working with. You can also just write out your variables and say, P is this distance in miles, C is this distance in miles. We have the rate of change in miles per hour. It's just somewhere you need to have it very clear what it is you're measuring and the units you're working with, right? So we can just put in here that this is in miles, C is in miles. The rate of change, therefore, is going to be in miles per hour. And this is radians, right? And then time is in hours, right? So time is in hours. So again, just making it clear each unit, what it's measuring and what unit it is in. So from here, we now need to come up with the equation, right? So we need an equation. So we're going to write an equation relating, we have P, C, and theta. So again, if we draw our little diagram, here's P, C, and theta. So once theta is involved, we know we're working with trig. And if we want opposite and adjacent, we're ignoring the hypotenuse. We are working with either tangent or cotangent. So this lends itself towards tangent of theta is equal to the plane distance divided by the camera distance. Now we're going to go ahead and differentiate with respect to t. So we have d dt of tangent of theta is equal to d dt of p over c. So at this point, we have a quotient rule involved. So derivative of tangent is secant squared theta, and then we would have times d theta dt. Quotient rule, we would do the derivative of p with respect to t, so dp dt times c, and then subtract p times dc dt. And this is all going to be over c squared. From here, we need to plug in and solve. So we know, again, that c is equal to 0.09 dot, dot, dot. I have that number stored in my calculator. P is equal to 0.75 at the point of time we care about. dc dt was equal to 4.54 dot, dot, dot. dp dt is equal to 350. We don't have theta, but we can do some right triangle trig manipulation to figure out secant squared theta. So if we work specifically with our right triangle, we have theta, we have, let me draw the triangle we did have. So we had this way. So here's theta, and then we had 0.09, 0.75. And then if I want secant of theta, right? Secant of theta is 1 over cosine theta. And so cosine is adjacent over hypotenuse. So secant should be hypotenuse over adjacent. So we could do Pythagorean theorem and figure out the hypotenuse would be the square root of 0.09 squared plus 0.75 squared. Again, 0.09, I'm just doing a shorthand. That number is stored in my calculator. Then we divide this by adjacent, which was 0.09. So secant squared theta would just be 0.09 squared plus 0.75 squared all over that 0.09. And then from here, we now have all the information we needed to plug in. So our equation was secant squared theta times d theta dt was equal to dc, which order did I do it in? dp dt times c minus p times dc dt all over c squared. So secant squared theta is the 0.09 squared plus 0.75 squared over 0.09 times d theta dt. And this is equal to dp dt was 350 times c is 0.09 minus p was 0.75 times 4.54 all divided by 0.09 squared. And so we're really looking at d theta dt is equal to the 0.909, one of those will cancel out, and we will have 350 times 0.09 minus 0.75 times 4.54 all over 0.09 times 0.09 squared plus 0.75 squared. And we can go ahead and plug that into the calculator. Again, the 4.54 and 0.09 are currently approximations. I will use the numbers I stored in my calculator to get the more precise values. So we wind up getting that d theta dt is equal to 549.46 radians per hour. Just note that any trig in calculus, all the derivatives in calculus and trig are based on radians for the angle measurement. So we will wind up with radians as our units when we're working with these. And if it asks for degrees, you would have to do unit conversion. So at this point now, we need to do a unit conversion to radians per second. So we're now going to convert to radians per second. So to do that, again, we have our 549.46 radians per hour. If you know the direct conversion of seconds to hours, you can do that, or you can pass through minutes. So if we pass through minutes, we'll put hours up top and minutes down below. And then we do minutes up top to cancel with minutes down below and seconds on the bottom. And this will give us our radians per second. So we have 549.46 radians per hour times 1 hour per 60 minutes times 1 minute per 60 seconds. And we wind up getting 0.15 radians per second. So if we put this all in final notation, what we get is that the camera is rotating at 0.15 radians per second at the specified time. All right. So again, this is more complicated related to it's probably just in the fact that you do have to watch the units. I know the trig can also sometimes cause complications. You're going to want to draw a lot of right triangles so you can kind of convert back and forth between the ratio version of the trig and the notation or the trig notation. But this is the same process as we were doing before, just with a little extra steps to do all of our unit conversions.